Hello guys, welcome to Kobe's Math Nook. Today we're looking at another concept on classification of ordinary differential equations. Ordinary differential equations can be classified based on 1. The order of the differential equation. 2. The linearity of the differential equation. 3. The homogeneity of the differential equation. Though we can also classify ordinary differential equation in other forms, but we are going to focus on these 3. And after getting to know all these concepts, we're going to use this concept to name an ordinary differential equation. So now let's look at our first concept, order of differential equation. Now we can say that the order of differential equation is the order of the highest derivative of the differential equation. So when we talk of the order of differential equation, we are referring to the highest derivative of the differential equation. The highest derivative of the differential equation. What do we mean by that? For instance, when we look at this differential equation, dy dx plus sine x is equal to 0. This differential equation, what is the highest derivative? It is what? 1. Hence we can say that the order is what? First order. First order. Another example that we can look at is, assuming we have this y prime prime plus sine x equals 0. Now, what is the order of this differential equation? You can see that this y prime prime simply means this is the same as this, the square y dx squared plus sine x equals 0. So when we say the order, highest order over highest order is what? 2. Hence we can say that the order of this differential equation is second order. Second order. Now let's look at another example on the order. The cube y dx cube plus the square y dx squared plus 4x e power y equals 100 sine x. Now let's check to see the highest derivative of this particular differential equation, and you can see that though we have the second order here, but the highest, the key thing is the highest derivative. The highest is what? The cube. So hence we can say that the order is what? Third order. I hope it's clear. So differential equation can be classified based on the order. Now let's look at homogeneity of the differential equation. Now, differential equation is said to be homogeneous if the dependent variable, the dependent or the unknown variable, and its derivative are made the subject, and after it being made the subject, it is equal to what? 0. Meaning that that particular differential equation involves mostly the dependent variable. So let's take some examples. Dy dx plus xy equals 0. So now let's ask ourselves, is this homogeneous or non-homogeneous? This is homogeneous. This is homogeneous. Why? Because this involves the what? The derivative of the dependent variable and a function of what? The dependent variable. Though there's x over here, but because the x is a function of the dependent variable, so it's what? Homogeneous. Now let's look at second example. What of this? Dy dx plus xy plus x equals 0. Is this homogeneous or non-homogeneous? This is not homogeneous because there is what? Independent variable over here, after we have grouped all the dependent variable and its derivative, there's still an independent variable in there. So this is non-homogeneous. Homogeneous. Now let's look at another example. Y prime prime plus 5y prime plus y equals 0, and this is homogeneous differential equation. Why? Because this is the derivative of the dependent variable, the dependent variable, and there's no any other independent variable in there, so it makes it what? Homogeneous. I hope it's clear. So that is the basic concept about the homogeneity of a differential equation. So always take note that there shouldn't be any independent variable after the dependent variable and its derivative has been grouped. That's very important. Let's look at the other example. The next example is the linearity and non-linearity of differential equation. Differential equation can also be grouped based on whether it is linear or non-linear. But on that, we need to consider these three key points. Very, very important. So we say that, note, for a differential equation to be linear, first of all, the dependent variable and its derivative. The dependent variable and its derivative, this must occur to the first degree only. First degree. Example is this. Y, if the y is a dependent variable, there shouldn't be any power over here. If it's y squared, it makes it non-linear. Y prime, there shouldn't be any power to it. If maybe we have something like this, or even cube, it becomes non-linear, meaning the degree for the dependent variable and its derivative is more than 1, so that becomes non-linear. Secondly, there shouldn't be any transcendental function on the dependent variable and its derivative. The question you may ask is, what is transcendental function? There are functions like the exponential functions. Exponential function is maybe you have a power x. That's the exponential function, or 2 power x. Whenever there's an exponential function on, the key thing is on the dependent variable and its derivative, it makes non-linear. So the trig functions like sine y, whenever there's any trig function on the dependent variable and its derivative, it makes non-linear. When the logarithmic functions, assuming we have log of maybe y base x, this y makes it non-linear. The inverse trig functions, the hyperbolic functions, all these are the transcendental functions that we're talking about. So we are saying that there shouldn't be any transcendental function on the dependent variable and its derivative. Thirdly, there shouldn't be any product of the dependent variable and its derivative. So the dependent variable, this, when you have something like this in it, it makes non-linear because this is the dependent variable, this is the derivative of the dependent variable, it becomes non-linear. So these are the three key important factors that you need to know when it comes to the classification based on linearity and non-linearity of differential equation. So let's look at examples of linearity and non-linearity of differential equation. Examples. 1. Assuming we have this, so we have y prime plus 3x squared y equals 0. Is it linear or non-linear? So now we said that for differential equation to be linear, 1, the dependent variable and its derivative must occur in first degree. So let's look at whether the dependent variable, this is the dependent variable, is it in the first degree? Yes. The derivative too is in first degree, hence it's linear. Another example, let's look at this. The square y, the x squared plus 3y plus x squared y plus 4x equals 8. Is this linear or non-linear? Let's check whether it follows the 3 rules that we stated. Is the dependent variable and its derivative in the first degree? If so, then it is true. Yes, this is in the first degree. Remember, this is the order. The square over here is order, is not in degree. So it's in the first degree. This also in the first degree. This also in the first degree. So that is correct. There's no transcendental function. There's no product of this and then its variable. So this is also what? Linear. Number 3. Let's look at another example. Y prime 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 power 4 plus 3x y prime squared plus 8y squared equals 4. Now let's check, is this linear or non-linear? Now let's look at the derivative. If the derivative to the power, the highest degree is 4, and you said the highest degree must be 1, hence it's not. So even this one nullifies it, the fact that it's linear. So this is straightforward, non-linear. Let's look at another example. We have sine x dy dx plus y equals 2. Is this linear or non-linear? Now, is the dependent variable and its derivative to the first degree? Yes, this is to the first degree. This is also to the first degree. Is there any transcendental function? Yes, there's a transcendental function, but the transcendental function is not applied on the dependent variable, but rather on the independent variable. Hence, this does not make it non-linear. It's still linear. This, if here was to be y, then that becomes non-linear. So here is what? Linear. Linear. I hope it's clear. Now let's look at another example. Let's look at this. We have tan dy dx plus sine s plus 2y equals 0. Now let's look at the difference between these two. This was applied on the independent variable, but this was applied on the derivative of the dependent variable. So meaning this one is that the argument over here is dy dx. So since that you have a tan of dy dx, now it means the transcendental function has been applied on the dy dx, and hence it is non-linear. I hope it's clear. So these are some of the ways in which we can classify the ordinary differential equations. Take note of that. Our next video, we are going to look at how to apply these three concepts to name a particular linear equation. It's a very important concept. Thank you very much for watching. Subscribe to our channel for more exciting videos. Bye bye.